we'll be talking about big data and cloud computing. Yeah, I may edit that other thing. So what I want you to take away from this lecture is, that there are a lot of buzzwords, right? There is big data, there is cloud computing, there is MapReduce, there is this, there is that. And what I see among students is a lot of confusion. They confuse one with the other. Is big data same as cloud, or is it different from cloud? It is not very clear to many people as to what it is. So in this talk, I am going to discuss what is big data and what is cloud. Two separate things. They are not the same. I don't want you to confuse, and why they came about. What was the evolutionary process through which cloud and big data came out, and what kind of things that are happening in that. We are doing a lot of research in big data analysis. We are also doing a lot of research in not cloud computing, but MapReduce and Spark for scalability. So the last two lectures will discuss MapReduce and scalability issues for some of the algorithms that we use. So the question is, we had DBMSs, they were working fine, they were managing large amount of data. What did we do? Why did we do more? So here is a slide that says DBMSs have served as enterprise data storage and management for more than 40 years. Mainly OLTP. OLTP means online transaction processing, which is different from OLAP, this online analytical processing. So typically OLAP is used in the context of data warehouses. OLTP is used in the context of relational DBMSs. So then came data warehouses have provided additional drill down and OLAP that has been integrated with this. So the capability of OLAP was not present in the traditional DBMSs. They could not do three-dimensional analysis. They could not do a lot of different kinds of analysis that are possible with OLAP. Then data mining does a different thing. Data mining has also been applied on DBMS data and data warehouses. Remember, I gave the example of the DB miner, which IBM developed. However, data and processing needs have evolved since the advent of relational database. That is what is giving rise to big data. We'll see. Scalability is important, and we will look at data scalability and processing scalability. Two different ways of scalability, and why DBMSs were not very good at these things and why one had to develop it. Especially data distribution, query optimization, concurrency and recovery is very complicated and difficult in multiprocessor system. That is why you don't see DBMSs working with very large number of processors. We do have DBMSs on 8 processors, 16 processors and 32, but you don't see them on 1,000 processors or 10,000 processors, which is a very different ballgame. So scalability, when we come to scalability, you can think of two things. One is the data scalability is accommodated by adding disks and larger disks. So if your data increases tenfold, instead of keeping 1 year worth of data, if you want to keep 10 years worth of data, you need more disks. Now adding disks may be easy, putting data on that may be easy, but processing them is complicated. If you use the same disk I/O for 2 disks versus 10 disks, then you slow down. Your performance will suffer. And you also have to determine which relation should go on which disk, how do you partition it. So there are a lot of complications with that. So this means long wait for I/O given the same number of processors. To overcome this impedance mismatch, you need more I/O throughput, additional I/O bandwidth. This has not been easy. Data partitioning and it need to be figured out. So doing horizontal scalability using a DBMS is not straightforward. It's fairly complicated. So because of that, other means like MapReduce has been developed. We will not discuss it in this lecture today, but we will discuss it in the subsequent lectures in this course. Then there is the computing scalability. This means I am adding more processors, or I am adding more powerful processors. Now, it's one thing to add powerful processors, and it's a different thing to feed data to those processors. So remember, in a DBMS, you have to stage data from disk to main memory in order to do processing, and that is the bottleneck. Memory is in milliseconds, processing data in memory is in nanoseconds. So there is a difference of 1 million times, and that is the big problem that one is facing today, because our disks are very slow. We have very large disks, we can put a lot of data, but you cannot do any processing on a disk. Any processing has to be done in memory, which means you have to bring the data, process it, and put it back on the disk. So that I/O is not increasing with Moore's law. It is not doubling every 12 months. It's a much slower thing. Now there is a solution on the horizon, that is the SSD, solid state disks. Solid state disks are much faster. Why? Can anybody tell me why solid state disks are much faster than HDD, hard disk drives? You should know it. You know SSD, you know HDD, but you know why one is better than the other. Anybody? What happens in a HDD?
We use cylinders.
Can you use the mic?
There's a stack of disks, and for every search of data, we have to go track by track, and every disk by disk, and then track, and then particular sector to fetch particular data.
Yes.
This is what happens in SSD, but I'm not sure about how SSD works.
Well, what you're saying is true, but I think the underlying reason is hard disk is a mechanical device. The platter, even today, if you have a laptop without SSD, there is a disk that rotates at 7,000 RPM or 10,000 RPM or 15,000 RPM. That is the limitation. The limitation is the mechanical device. You cannot make it rotate faster and keep the accuracy of data flow. Yes, sector and all those things are there, but the basic reason is that it is a mechanical device which has to rotate. So now compare the rotation of a jet engine, which rotates at about 40,000 RPM, whereas a disk rotates at about 10,000 RPM, and they have not been able to increase the rotation speed. That is the real bottleneck. Whereas in a solid state device, there is no mechanical part. There is no mechanical part. So in the absence of a mechanical part, this mechanical equation is taken away. There is no rotating disk. You can access things much faster. So SSD is faster for one reason, that there are no moving parts. But they are very expensive right now. They are very expensive, and there are certain limitations. For example, in an SSD, there is a limit on the number of read to writes. It's about 2 million or 3 million, but still there is limitation because at the end of that, it won't function. So there is a lot of work done in the database area moving from HDD to SDD. So how can we improve the database performance, efficiency, storage when we use SDD versus HDD? That's a big research area today because SSDs are going to be here. They are going to become cheaper as volume increases, and then lots of people will, my laptop has 2 terabytes of SSD, which is very fast, but it's very expensive. So you cannot afford a lot of disk space, and hence still a lot of data is stored on HDD. Okay, so understand the basic difference. So when you increase the computing speed, the bottleneck remains the same. The processor can process faster, but data is not flowing. It is like a 3-lane highway merging into single lane. Then there is a backlog. So then it has to wait. It has to wait for the data to come. So this is the real problem which we call impedance mismatch. So we are going from traditional databases to big data. So this is just a picture I wanted to put. This is not a fully correct picture because I say it clearly, it is not just about the size. We'll see what it is. It is about the diversity of data. It's about holistic analysis. These are very different from what we are doing. Certainly the size is big. You need more processing. You need more processing power and other things, but the size is not the only thing. So then what is it? So this is how big data is characterized today. They are known as 4 V's. Volume, velocity, variety, and veracity. So these 4 characteristics define what is big data. This is how it started. Today, I have seen in the literature people are adding anything that starts with a V. They are adding variability, validity, vulnerability, volatility, blah, blah, blah. But I do think that these are the basic fundamental differences. So what are these? Volume. Volume is the size. Now we know how to deal with volume. I mean, databases deal with terabytes of data, so we are capable of dealing with volume independently. What is velocity? Velocity is the rate at which data is being generated. So this can be from sensors, which is sending every 30 seconds data 24/7. You are monitoring various things, battlefield monitoring, infrastructure monitoring, environment monitoring, whatever it is. It is also true for things like Facebook and Twitter. In Twitter, whatever the opinion or sentiment that is analyzed is only valid for 15 minutes. Afterwards, there is a new sentiment because data is changing constantly. So we know how to deal with this because we have developed something called stream data processing system. I have done some research, and we have done a lot of research where you can process data that is coming in at a very fast rate. Now remember, processing data with velocity is very different from processing data in a DBMS. Here, the assumption is data doesn't change. I mean, it changes but very slowly. So if you take a university database, it changes every semester, but it doesn't change every second. So you don't have the same kind of quality of service requirements as you need for velocity. So there are systems today that have been designed and built. They are known as single pass algorithms that deal with stream data. So battlefield management is a good example where a soldier wears 20 to 25 sensors on his body. These sensors continuously transmit different information, his pulse, his heart rate, his hydration situation, whether he is standing vertically or he is not standing vertically, whether his gait is slow or not. Now, if you have 50,000 soldiers, each with 20 sensors, and each of them are sending information every 30 seconds, imagine the amount of data you are going to get. And how do you process that? So you want to detect whether somebody is fatigued on the battlefield so that you can remove that person immediately. You want to identify people close to him who are not fatigued. So stream data processing is a very useful. This can also be useful for highway traffic. For example, if there is a traffic congestion, it can detect traffic congestion and reroute traffic, for example. It can be used. It is also similar for twisted traffic. So we know how to deal with velocity separately. Come to variety. What is variety? Right now we have been dealing only with comma separated data, numeric data, tabular data. But we have images, we have audio, we have video, we have EKG, we have various other kinds of data. That is variety. Now we know how to process each of them individually. There is a lot of work in image processing, there is a lot of work in video processing, there is a lot of work in identifying cancer in various MRI scans. We know how to do it individually. Velocity is something a little bit more complicated. Velocity means how good is the data, confidence in the data. It is not that every data is equally good. I mean, a good example is the CIA data or espionage data. So there you get a lot. There is something called human intelligence, and this human intelligence comes from various sources, and the confidence in the human intelligence depends upon the source. How good is the source? What is the track record of the source? So that's very important. So there is work in probabilistic databases, statistical databases, where you assign a confidence to the value you have in the database, and then you do computations or same SQL query computations, and then you also derive a confidence for the result. So if you use data with different types of confidence, what will be the confidence of the resulting solution that you are seeking in the query? So what is important to understand is we now know today how to deal with each one of them separately. But big data analysis says that we want to do all of that together. So a good example for that is a healthcare issue. So if you take it, the healthcare, so you have a person's demographic information, you have a person's pathology reports, you have a person's x-rays, you have EKG, you have various videos, colonoscopy, this, that, scans. Now you need all of that to understand what is happening in this person. Even today it is not done that way because doctors do not have access to all the information about a patient. They have fragmented, partial information about a parent. So they make judgments based upon that. But that may not be completely correct because they don't have all the information. But if you have all the information, then you can do something called personalized healthcare. And then if you have this data for the whole community, then you can also do aggregate analysis for community. You can find out which age groups have a high incidence of this particular thing, or which ethnic groups have high incidence of this thing. All those analyses are possible if you have all types of data and you are able to process them together as a whole, not piecemeal, not individually. Okay, this is the challenge of big data analysis. So, is it clear? I made myself clear. What is the difference between what we are doing today versus what big data and big data analysis is? So big data analysis is a process of inspecting, cleaning, transforming and modeling large amount of disparate data. That means different types of data with the goal of discovering useful information, suggesting conclusions and support. So this is what we call holistic analysis. Instead of individual analysis, you want to do analysis together on all the data, and that is why it is called holistic analysis. Of course, there is connection to data mining. It is not very different from data mining, except the details, the data types are different. So analytics include both data analysis and communication. Analytics is not so much concerned with individual analysis, but with the entire methodology. So this is what you need to understand as to what big data is, what big data analysis is. So big data is just a collection of different types of data that are together as a whole, and then analysis on them now has to be done across the data, not vertically. So where do you get big data? I have already mentioned Hadron Collider. It was initially generating 10 petabytes per year, and it was supposed to generate 1000 petabytes and in 10 years. It has been more than 10 years. 2,500 physicists are collaborating in analyzing that data. These are the people who found the boson or the God particle. Large Synoptic Survey Telescope, again large amounts of data. This is another telescope which is used by the US Air Force, generates large amount of data, satellite images, metadata, other information. It also comes from commercial sources. You have billions of camera images, video uploads, web usages and other things. You have YouTube, you have other things. So today there is a push. We are also doing some research on big data analysis, and as we have done on individual things. So there is also large amount of dollar value associated with various sectors. US healthcare, Europe public sector administration, global personal location data, USGS, utility manufacturing. So the big picture is, this is sort of my view. So now, remember I showed you an earlier picture with a similar inverted triangle. There we were feeding raw data, one type of data. Now into the same box, we are feeding structured data, image data, video, audio data, unstructured data. Now you have to generate inferences using all of them, not just one of them. This is the real challenge of big data analysis. And it is not easy, and we are nowhere near it at this point in time. A lot of people are working on bits and pieces, are trying to figure out what model is useful for this, what kind of techniques and algorithms you want to use. So there is a whole science, what kind of abstractions are useful, machine learning, neural networks, what kind of analytics are useful, video processing, stream processing, communities, hubs. We'll see a little bit of, so my view of big data analysis and science. And here are the, what I call, so instead of deriving it, like in mining, we were either doing classification or doing clustering or doing KNN. Here, there are analysis expectations. You may want to ask different types of questions, not necessarily questions because you cannot write a query for that, but this is what I want to get out of this. Is it possible? Not everything you want to get out of that may be possible. We may not have the algorithms to produce it or algorithms to compute it, but this is the big picture. I also want to emphasize that the result of that, you make decisions, real world decisions, real decisions that needs to be very important. You are also looking at trends and predictions. You are extracting knowledge, you want to understand the knowledge. Visualization becomes very important. Not just deriving 1000 numbers. So this is what, to me, big data and big data analysis is. Trying to figure out a holistic way, transforming instead of one piece of data or one type of data, multiple types of data into actionable knowledge and decisions. So again, data science today tries to do something similar, just like the one I showed for the mining. You can see that for data science, in addition to other things, you have different components. You have computer science, machine learning, mathematics, statistics, probability, software, powerful software, business or application usage. All of this have to come together to perform data science, data analysis or big data analysis. And this is the key. Now, I think there is hope that we are at a point where all of these things, like we say, the stars are aligned and you may be able to do something that one could not do earlier. So just to give you an understanding of what is it. So we started a data science program, a master's in data science program at UTA 3 or 4 years ago. And I was involved in this. I was involved in the development of the courses for that. I also taught one course for 2 or 3 semesters, and now others are teaching that. It's going very well. There's a lot of interest. So we take students from multiple domains. So the key in data science is that you can analyze data from any discipline. I have had students from mechanical engineering, aerospace engineering, biology, social sciences, and electrical engineering, because everyone needs to do data analysis. Their data sets are different, the domain knowledge is different, but analysis is common. Analysis doesn't change much, slightly maybe, not very much. So it's very important in a data science program that you have people from different backgrounds, because they can go back to their domain and apply data analysis in their domain. A computer science person may not be the right person to go apply data analysis in a biology domain, because you don't have much understanding of biology. So that's very important. So data science or analysis is not new. Data collection, storage, management, query search, all of them. Emphasis was on understanding and managing data. Now data mining brought an exploratory and discovery component, first on samples, later on real world data. Now we are combining all aspects of application, business with CA statistics to holistic knowledge. So again, it's not a single approach or a single solution. There is no silver bullet. In my view, using extending current approaches and developing new ones, a suite of approaches, if you will, for modeling and analyzing a diverse complex set is important. So, if you want to define the problem in what you are given and what you want, what is given is a complex data set, maybe from different types of data, and a set of analysis objectives, and what you need to do is determine modeling, what abstractions are needed, what kind of analysis methods are needed, and what kind of visualizations are needed. So this is the problem, this is the approach that you want to use for solving that. And I stress modeling because many times we have this tendency to go from data to applying algorithms directly. But you don't know how it works. So always, just like we use, I don't know if you are familiar with entity relationship diagram, for example, it's a model that will allow you to disambiguate a lot of things in your specification and then translate that in an algorithmic way into a schema that you want to process on. So some intermediate representation modeling, it doesn't have to be ER diagram, it can be a graph, it can be a multi-layer network. We'll see some of them later. So that brings us to the big data analysis. Now you may have a question on what is the difference between mining and big data analysis. So here is my view of the difference between that. In mining, you are taking a data set, a specific data set, and applying a specific mining algorithm, and then getting the results. Whereas here, it's much more broader. It's much more broader. You have data set description, but these are from an application of different types, analysis objectives. You use a model, maybe we have done some work in ER to MLM, so I have put it there. So you need a model, and then you generate analysis expressions, you compute analysis expressions, you drill down, and you visualize. So this is the complete life cycle, including knowledge engineering, deriving data, and then going to modeling, analysis, expressing the objectives, and visualization. So this is what I think differentiates traditional mining from big data analysis. Any questions? No? Okay. So I may have this later. So let's come to the cloud. So what is cloud and what is cloud computing? Again, as I said, don't confuse between these two. These two are not the same. So this came about around 2000, evolved from grid computing with improvements. So we had grid computing, we had cluster computing. By the time cluster computing, server farms, and use of commodity components had become commonplace. So this is very important. So this commodity component. So now both grid computing and cluster computing became a reality only because of commodity components. What do I mean by commodity components? So this was pioneered by one of the computer science faculty from Berkeley. And commodity components is, so remember I showed you disks which were very huge, very expensive. At some point, this guy said, this doesn't look right. Can we produce disks on a smaller scale that are like commodities, like you can buy it cheaply, and even if they are not as good, it doesn't matter because I can buy lots of them, and even if some of them fail, it's okay. So today in a cluster, you may have thousands of disks, and then RAID was invented to make sure data is not lost. Even if there is a failure, single disk failure, you can recover the entire data. So commodity disks, commodity components made grid computing and cluster computing possible, which was not possible before. Improvements and advances in hardware and software, networking was more robust, and bandwidth kept increasing. So I don't know how many of you have used modems. We had modems at some point in time. We were calling up a server with a dial-up modem with a baud rate of 56K, and then they were sending text data across the wire, across the telephone wire, and processing them. And due to internet accessibility, fluctuations of access usage became much larger. We'll come to that. So what is the path to cloud computing? We started with mainframes, I showed you. You can actually think of this as primitive cloud computing where you are not accessing it on the web. You are going physically to a computing center which had a very powerful computer and getting your job done. Today that's what you do on a cloud, but you don't do it over the network. You do it over the web. You don't have to go anywhere. You don't even know what is in the cloud. Then came desktop and PC revolution in the 80s. Then came high performance computing and supercomputers. So you might have heard of, CDC and Cray computers. They were very expensive and they were being used. Then came the internet. After this, because of the internet and the network robustness, came grid and cluster computing. Then came cloud computing. So what is the need for cloud computing? Why is cloud computing touted as the solution, and what was the problem? So here is an example. Consider the official Wimbledon site. Most of you or all of you should be familiar with Wimbledon. This site gets extremely high traffic in the 2 to 3 weeks when the championship happens. For this 2-week period, the site will have high server usage. For the rest of the year, the site will have low traffic and hence most of the resources it's idle. So this was the real problem. In order to serve 2 weeks in a year, you had to maintain all the equipment, all the infrastructure for 1 whole year, paying the cost, bearing the cost. Spare capacity need to be maintained or leased from somewhere. So there is a lot of spare capacity, right? Because you provide resources for the peak demand. But when the peak demand is not in peak, most of the resources are idle. And spare capacity need to be maintained. Or you have to obtain it from somewhere. This is what is called internet scale elasticity, meaning you want the flexibility to fluctuate between high demand and low demand, not wanting to maintain the same level of cost. This was also true for companies, IT companies. They were maintaining a lot of equipment and they were not being utilized. The traditional approach is to keep enough spare capacity to deal with the needs of 2-3 weeks. It's expensive. Hardware gets old and obsolete. As you know, in our world, 2 years is too long. You need to replace hardware every 2 years, and then you have to replace software. Hardware gets obsolete. Maintain and manage people, software acquisition and maintenance. It was not easy or possible to outsource this just for 2 weeks. So there was no ways to say, can I outsource this, my Wimbledon site, for 2 weeks when there is peak demand. It was not just IT shops were maintained that were quite expensive. So this was the situation. So the question is, what is the solution to this situation? These situations and needs were a side effect of internet availability and ubiquitous storage. So this demand for Wimbledon servers was mainly because of the internet, right? When there was no internet, people were reading newspapers. Millions of people were not looking at the site. So internet created this problem of easy access, immediate access, 24/7 access. And that had to be maintained. Making things available on the web was critical. Enterprises were maintaining expensive IT shops with all the costs and headaches that came with that. So cloud computing became the answer for that. So how did it become the answer? Could not be done earlier due to technological limitations. So this is also very important to understand. As I said, sometimes our expectations move faster than what technology can provide. It doesn't happen. Technology has to catch up with that. So reliable networking, large bandwidth, management of clusters, privacy, software as a service. So all of them had to come together in order to make cloud happen. So what are the components of a cloud computing environment? There are 4 components. The first one is what we call thin clients, or clients with a thick swing switch. I'll come back to that. Second component is the grid computing. What is grid computing? Ability to connect disparate commodity computers to form one large infrastructure harnessing unused resources. This is important and very much required. Today, you know AWS, you know Azure, you know what Google provides. They all provide this capability. These two were already there. These are not new. These two are new. Very specific to cloud computing and very different from what we were doing before. What are they? Utility computing. Paying for what you use on shared servers like you pay for public utility such as electricity, gas and water. This was not the case before. You could not go and rent a server and say, I want it for 2 days. I'll only pay for 2 days. That was not the case. So in cloud computing, this is one characteristic. So you can rent, and like electricity, gas and water, so when you turn on electricity, you don't go and ask anybody, should I turn off my air conditioner? You don't ask, right? You just turn it off. You assume that somebody is willing to provide that. And that is on-demand resource provisioning. You can demand resources at any time you want without prior intimation. You can say, I want 100 computers. Okay, that's not enough. I want to increase it to 500 computers. You don't have to tell anybody. It will be made available to you automatically in this environment. And that is the difference. Whereas in earlier, IT shops were localized. Every company maintained their own IT shop. Somebody else's IT shop could not access your IT shop, even if it was idle. That was not allowed. So these are the characteristics. Utility computing, on demand, not static, no need to indicate resource requirements ahead, ability to add and remove computing resources. I'm saying resources. It can be network bandwidth, it can be software, it can be hardware, it can be disk, it can be anything. Not just CPU. So what is thin client? I don't know whether some of you may be aware of what a thin client is. So when we used to communicate with the server on a modem, we had what is known as a dumb terminal. I don't know whether any of you have heard of a dumb terminal. It was really a dumb terminal in the sense that it had no processing capacity. It would only transmit information to the server and then put the information that it got from the server back on the screen. That's all it was doing. But today, we don't have dumb terminals. But that's why I put with a thick switch. So your laptop can act as a dumb terminal. In fact, that's how you use your laptop when you access the web. Your laptop is not doing anything. Everything is done at the other end. It is just sending information for display. And your laptop is displaying, or your tablet, or whatever it is. So you don't even need a powerful machine for cloud computing. You just need a device which can interface with the server, and if you want graphics and other things, yes, you need more powerful machines. Grid computing, this is also not new. This has been around, but it has been pooled in such a way to make utility computing on demand possible. Any questions? So I'll just explain what a thin client is, so I'll skip this. I have also explained grid client. So grid client was used for a very long time. Especially people from other disciplines, physicists, people who are doing genome work and other things, they needed very large amounts of computing for cancer research and other things. So grid computing was very, very, very popular at some point. In fact, at some point, some of the researchers would even ask, hey, are you willing to donate your laptop or desktop time when you are not using it so we can use it and do some computation? And that was also going on. Another example is, for example, mathematicians are very fond of computing the next prime number. Now, they have computed prime numbers up to maybe 300 digits now. We don't know how many digits the next prime number is, but that computation is very expensive because you have to keep checking every number. So all those things require tremendous amounts of resources. That's why grid computer and Condor, other things came into picture. And the important point is pay as you use. Pay as you use is a concept that we used only for utilities, water, gas, electricity, not for computing. Now, this is just a historical perspective. For those of you who may be aware, Sun is no longer a company. It was acquired by Oracle, but it was a very big company at some point in time. At some point was shipping servers with extra CPUs that could be brought into use as needed. You would not be paying for them until you use them. So they would send you a machine with 16 CPUs. You can today turn on only 2 CPU and pay only for 2 CPU. Later, if the demand increased, you can turn on 2 more CPUs and pay for that. So this is a very primitive way of pay per use. Cloud is a generalization of that. Cloud supports pay as you go for individual components such as CPU storage. So here is a diagram about the relationship of supercomputers, distributed system grids. So here is one. There are lots of definitions of what a cloud computing is. Cloud computing has the following character: the illusion of infinite computing resources. That means you can get any amount of resources you want. You don't have to own it. The elimination of upfront commitment from cloud users. This is on-demand provisioning. The ability to pay for use as needed, pay per use provision. So cloud computing makes computer infrastructure and service available on demand, on need, or on demand basis, like utilities. The computing infrastructure could include anything: hard disk, development platform, database, computing power, complete software. To access resources from the cloud, vendor organizations do not need to make any large-scale expenditure. This is very important. So, there is something that we call what is called the leveling the playing field. The difficulty for smaller companies earlier, apart from IBM, Microsoft and others, was entering into the market. They had to spend a lot of capital expenditures to set up IT shops. Now with the advent of cloud, all of that disappeared. Anybody could rent the minimum number of resources you need in a very cheap way. So organizations need to pay per use. That is, organizations need to pay only as much for the computing as they use. The billing model of cloud is similar to that. So there is a vendor, there is an organization which is the user. So this is important to understand. In the traditional IT, If somebody is a business management here, they will understand there are two kinds of costs. Fixed costs and variable costs. Fixed costs are also known as capital expenditure. Like for example, building this auditorium is a capital expenditure, one-time expenditure. But maintaining this auditorium on a daily basis is variable cost, operational expenses. So in an IT company, you have both of these. And unlike this auditorium, which is going to be here for a long time, computers don't last for a long time. They have to incur fixed costs every 3 years. Now with cloud computing, this whole fixed cost is eliminated. There is no fixed cost. You just rent. So if NIT allows people to come and rent this auditorium, it becomes a cloud computing example. They can come and rent it for a week, conduct their seminar, pay NIT and go. You can easily convert it into cloud computing and make money. So coming back to our Wimbledon applications, in general, the usage of computing that can be increased or reduced on need basis is called elastic computing. So computing requirement varies. So this elastic computing capability is provided by cloud. Now, Wimbledon can just lease 100 CPUs for 2 weeks and then reduce it to 2 CPUs. So the total cost is reduced. So some of the applications, Hotmail, for those of you who may be familiar, was launched in 1996. It is widely considered as the first cloud computing application, even though cloud computing itself became popular a little bit later. The data is stored at the vendor servers and users could pay incrementally to increase disk space. Google still has that model for increasing the disk usage, also known as leveling the playing field or barriers to entry. So cloud computing has really removed barriers for entry to the marketplace. Twitter, MySpace is gone. Wikipedia, YouTube, Facebook, LinkedIn, Google, everything today can be seen as cloud application. Companies that provide hosting services are also cloud services. Perhaps Salesforce.com is one of the best examples of cloud computing usage. Started in 1999, they only use cloud. Everything they do is on the cloud, there is nothing else. They are very good at customer relationship marketing. CRM company was the first successful example of providing software as a service in the business to business domain. Salesforce is a CRM tool for sales executives providing features like customer. Google, Microsoft, Amazon, everyone provides it. Since the cloud vendors provide services on the web, these are available from any location. So that is the difference between the old way of doing it and the new way of doing it. Cloud computing can be ordered online without detailed formal contracts. Cloud computing provides a level playing field. An example of Mozy Online Storage provides online backup. Now everyone does it. So, sort of trying to wrap this up. So now today, cloud is very prevalent. Everyone is using the clouds. I mean, may not be everyone, but a lot of people are using the clouds. So there are different types of clouds. Here is a list. Public clouds. Public clouds means anybody can use that cloud and put your data on that, and it's accessible to everyone. You also have private clouds, means these are very specific clouds set up for specific purposes. So for example, I know US Department of Defense, Air Force has its own cloud, military has its own cloud, and Space Force, they are private clouds that cannot be accessed by anybody else for privacy, security, various reasons. And you have hybrid clouds. You can have hybrid clouds, and interestingly, there are community clouds. So for example, many states, state of California has its own cloud. So everything that is done, all the paperwork or digital work, everything that is done in the state of California is on their cloud, which can be accessed from anywhere. So cloud, yeah, I'm sure even here perhaps NIC here provides such kind of capability. So you may have something like that here as well. So this is becoming very common, and you can see that here. So services, you can provide infrastructure as a service, you can provide platform as a service, you can provide software as a service. I just have a line on one of these. So today there is no limit to what you can provide as a service in a cloud. So cloud is kind of an abstraction. It has certain characteristics. As long as those characteristics are there, you can use it and do that. So to summarize, essentially a paradigm or a model where capital equipment, management and maintenance can be rented instead of owning on a need basis. So this is also to some extent outsourcing does that in a way, but for a different purpose, for a different reason. For raw commodities such as CPU, storage and bandwidth, this is straightforward. In fact, most hosting websites use a similar model, but they also provide different levels of development tools. You can ask for DBMS on that. You can ask for MATLAB. You can ask for any software that you want that can be provided. However, it would be very useful if you can also support a transparent programming paradigm to use these resources effectively. So this will lead to, in a couple of lectures, our MapReduce paradigm. Okay, I think this, oops. Okay, maybe this is the end. So I'm going to stop here today, and then I think we'll break for lunch, and then there is one more.